Hi everyone, my name is Eric McDevitt, and today I'll be presenting my final project and computational challenge for advanced data science. My project is titled Music Genre Classification, Traditional versus Deep Learning Approaches. My goal for the project will be to create some machine learning algorithm that is able to classify songs by their genre. Systems like these are used in music recommendation engines and playlist curation systems. And for both of these, you need automated genre tagging. So a stakeholder like Spotify, for example, can improve on these areas and proceed to sell more subscriptions and make more money. For this project, I'm using the GTZan dataset, which is a widely used benchmark in audio analysis. This dataset contains 1,000 songs, each belonging to one of 10 possible genres. There are 100 samples per genre, meaning this is a perfectly balanced dataset. Each sample is represented both as a series of features describing the harmonic and rhythmic devices in the sample, as well as it is explained by a spectrogram, as you can see on the right. Now, for a spectrogram, the x-axis represents time, the y-axis represents a spectrum of possible frequencies, and the color denotes the presence of any particular frequency for any given moment in time. Now, before we begin, some ethical considerations with this dataset. The first is that it's publicly available, so transparency is highly promoted with this dataset. Likewise, I will be citing the source to this dataset at the end of this slide deck. Now, this is a balanced dataset, which means that a machine learning model won't be biased toward any of the 10 selected genres. So this is good news. However, because there are 10 genres selected, they necessarily had to exclude some genres when curating this dataset. And so the means by which genres were chosen may reflect some sort of cultural bias based on what was familiar to those who created the dataset. My approach will be separated into two segments. The first is to take the tabular dataset and train traditional machine learning models for classification. The second will be to use the spectrogram data, which is simply a series of images, and use a convolutional neural network to perform classification on these. Convolutional neural networks are well known for their performance on image classification, so this is a clear choice with the spectrograms. It will be interesting to compare the performance of both of these, seeing as the spectrograms and the tabular data are both derived from the same wave files. So it's likely that one format may retain more important features of the data than the other, and this may be reflected in the accuracies of both approaches. So, the first thing that we'll talk about is the exploratory data analysis. And so starting with the tabular data set, I wanted to inspect the relationship between different features. And so the first thing I did was generate a correlation matrix that you can see on the left. This helps me identify which features may contain redundant information. And a lot of these pairs of features that were redundant were identified as well and confirmed with the principal component analysis that was used later on for feature selection and dimensionality reduction. On the right, you also see a pair plot of features, and so this allows me to use scatter plots of different pairs of features to analyze the distributions and the relationship between those features. I use a color map to separate each genre, and from this I'm able to derive a collection of interesting conclusions. For example, in most cases, metal and classical music samples tended to cluster on opposite sides of the distributions from one another, and the conclusion here is that these genres will likely be comparatively easy to predict, and it should be unlikely that these get mistaken for one another. I also generated a series of box plots for several features separated by genre. And one conclusion here was that I found in most cases classical and metal had the tightest distributions, which may indicate that they have a very defined sound. Now, moving on to the spectrograms, the first analysis I did was to compute the average spectrogram across the entire dataset. You can see that there's a clear distribution across the y-axis, again denoting frequencies, and this distribution favors frequencies around 225 Hz and decreases in intensity as you deviate from this point. You may notice as well that the y-axis appears inverted with the highest frequencies at the bottom of the spectrogram. This is a convention for spectrograms, though, in audio analysis, so I will reflect that with my visualizations here. The goal of creating the average spectrogram of the entire dataset, though, was so that I could then compute the average spectrogram per genre and see how each deviates from the norm. So here you can see just that. It's a series of spectrograms. Each is the average spectrogram for each of the 10 genres. And you can see that there's a lot of variance, which is great in terms of prediction later on. So some key takeaways: classical has prominent intensities across the majority of the distribution of possible frequencies, which is likely due to the diversity in instrumentation in this genre. For example, like a tuba and a flute fall in very different registers, and so these should be separated but both present. Classical also has the most obvious horizontal banding, probably again due to the fact that instruments are generally constrained to their own registers. And then another thing I noticed was that metal and rock have similar average spectrograms, except for the fact that metal has a section of higher intensity toward the middle of the range. I also generated some descriptive statistics for the intensities of the spectrograms found in each genre. And so you can see that straight away, classical again has the lowest median intensity. This is fairly straightforward to be expected. On the other hand, you have metal, which has a vastly higher median intensity than all the others. And so this indicates that metal tends to be a bit of a louder genre compared to the others, with all frequencies being utilized. Now, as far as pre-processing, I started off with the tabular data, and the first thing I did was check for any null values, and I was able to confirm that there's no missing data in this dataset, so no imputation was necessary. I also removed the file name column altogether because it contained the genre and label of each sample, and the rest of the file name was just a sequential index, which wouldn't contribute any valuable information in prediction, and even that could contribute to data leakage if the data was not shuffled before prediction. The next thing I did was standardize the data set so that all features would have a mean of 0 and a standard deviation of 1. This just ensures that any distance-based models won't be preferential toward any particular features, paying more attention than it should to some features based on their distributions and range of values. Next, I used principal component analysis to reduce the feature set from 58 all the way down to 20, and I chose the 20 that maximized the explained variance that was kept. And finally, I chose not to perform label encoding for the target because this would map each genre to an integer, imposing an ordinal relationship on the target vector. And genre does not have an inherently ordinal relationship, so I chose not to do this. Now for the spectrograms, the first step I took was to convert them to grayscale. The original spectrograms are described in color with 3 channels, R, G, and B. However, intensity is inherently one-dimensional, so storing it in 3 dimensions simply to support a color map is introducing redundancy and unnecessary complexity to the data's representation. Flattening it to grayscale should simplify the data while not losing any information at all, allowing a neural network to learn from the patterns in the data that matter the most. The next thing I did was apply random image augmentation to the dataset in order to artificially increase the size of what was otherwise a pretty small dataset. So adding these augmentations should should also have the effect of improving robustness to potential audio distortions and noise in the dataset. Then I removed the white borders from the images, which somewhat annoyingly were different in width on each of the sides, so it was a little bit more annoying to handle than it needed to be. But lastly, I resized the data to make it a square 224 by 224, and this will just be more suitable for our convolutional neural network in a minute. But now, pre-processing aside, it was time to select models, and I've already decided for the deep learning aspect of this project that I wanted to use a convolutional neural network, but for the traditional models, which will be trained on the tabular data, I started off with support vector machine. And so this model will attempt to find an optimal hyperplane that separates the two classes, or the 10 classes in this example, 2 in the visualization that I have there. But the reason I selected this was because our data set has a ratio of feature set size to the number of samples that lends itself toward overfitting. The ratio is 1 to 50, and so because of this, I want to be sure that any models I choose can help fight against this overfitting that I expect to encounter. And so SVMs are known to perform well in high dimensional data, which should in turn help fight that overfitting. Secondly, I chose k-nearest neighbors because I wanted to integrate a distance-based classification. And so my insight here is that I expect each genre to have its own cluster in the feature space. And even though these might not be disjoint, hopefully it should be separable enough that by using a simple voting mechanism, we should be able to classify each new sample. Finally, I used logistic regression as the third model because this has regularization techniques built into the model, and this can help prevent overfitting, which again was one of my concerns going into this. So now with those selected, it was time to train the models and optimize them for accuracy. And so to do this, I started off with the SVM, and I performed a grid search on kernel, C, the regularization parameter, and finally gamma. And I used cross-validation for all of the models again to really fight that overfitting. The optimal set of hyperparameters is what you can find in that table, and this resulted in an accuracy of 67%, which was pretty good as a baseline. Now, the confusion matrix at the top right can indicate how each genre was classified, either correctly or incorrectly. And some insights here are that country was often misclassified as blues, which should make sense as those two genres have similar historical roots. So it's likely that these could be construed for one another, seeing as they diverged not all that long ago. Disco is often misclassified as hip hop, which I found interesting, but maybe the instrumentation is a factor there. And metal had almost perfect performance. Now, again, I was sort of suggesting in the beginning that metal might have good performance as well as classical. Classical wasn't quite as good, but it was still pretty good, and metal was almost perfect. So the classification metrics in the bottom there can also give some interesting insights. One of which is that hip hop had a much higher recall than its precision, meaning that while the model was able to correctly identify a high proportion of true hip hop samples, which gives you that high recall, it also tended to incorrectly classify a number of genres as hip hop, leading to a lower precision. So that was pretty interesting, and the next step was to compare this against k-nearest neighbors, again performing a grid search on the necessary hyperparameters and ultimately achieving a marginally higher accuracy at 68%. The confusion matrix gives some of the same trends, good performance on classical and metal, and slightly worse performance on disco and pop. So this was an interesting result to see. It seems to make some of the similar choices to SVM which could reflect trends in the data itself, not necessarily in the models and how they interpret that data. Now, finally, I had logistic regression, which I trained using a couple of parameters here that I did a grid search on. And the optimal accuracy in this case was notably lower than with the past two models at only 62%. This, again, was a model that made similar mistakes to the first two models. For example, mistaking country songs for blues. Performing well in metal was one of its trends. But it simply made more mistakes across the board. And so this led to a lower accuracy. Now, if hypothetically we could increase the size of the data set and expand this beyond the 1,000 samples we have, we see that each of the models would benefit in a relatively similar way, which is that the test score would continue to rise slightly, but you can see by that orange curve that the testing score for each of the models is actually pretty close to an asymptote at this point. So based on this, I concluded that for SVM and k-nearest neighbors, these would be the models most worth pursuing because despite having a similar room for improvement as logistic regression, they have a higher baseline accuracy. So for this reason, logistic regression doesn't seem feasible to pursue because it's not going to improve enough to close that gap. Now, the next portion of this experiment was to work with the convolutional neural network. And the first thing I did here was train a baseline model just on my M1 MacBook Pro. Now, this trained for 15 epochs in about 30 minutes and had a poor accuracy at just 57%. And doing this allowed me to identify two fundamental problems with the convolutional neural network I trained. The first is that a convolutional neural network just requires a lot of data to fully catch on to different trends in the images. And so the solution here is to use transfer learning so that we can take advantage of the first few layers of a pre-trained model to catch on to fundamental patterns like textures and edges, but then we can fine-tune the additional layers of that model to capture domain-specific trends in spectrograms. Now, the second problem was that training even a small model just once took 30 minutes, and so iterating upon this would be a painstakingly slow process. So the solution here was to use distributed training on multiple GPUs, and for that I used Paperspace. Now, to return to the idea of transfer learning, I used the VGG16 pre-trained network as a starting point, and this is a network that's trained on the ImageNet dataset, and it's known to generalize well, acting as a baseline for models that can extend it to more specific domains. So I froze the first 10 layers, keeping those weights the same as they came, and those will be responsible for the more fundamental patterns in the images. Now I unfroze all the remaining layers of the VGG16, and this allows us to fine-tune those weights for this specific task of spectrograms for musical genre classification. Finally, I added some layers as output to the VGG16 network. I added dropout layers, which should help with overfitting, a flattening layer just for reshaping, dense layers for more feature learning, and finally a softmax output layer with 10 neurons, which will act as our classification. Now for the distributed training, I used Paperspace, which allowed me to connect to a dual A6000 instance. And you can see the specs of it at the top right of this slide. It is a very powerful set of GPUs that, if I wanted to purchase for myself to run this experiment, would cost me over $12,000. So to be able to run my experiments for under $4 an hour was a fantastic deal. I used Keras Tuner to find the optimal set of parameters for the model, and once I had that, Then I used TensorFlow's mirrored strategy to perform distributed training, which allowed me to increase the epochs from 15 all the way up to 50. I also increased the batch size, which should help with model convergence and stability. And all of this resulted in the training taking only 3 minutes, down from the 30 that it took originally. So the results of this training are what you see here. We achieved an accuracy of 77%, which outperforms both of the other models by nearly 10%. And so this was a very promising result. You can see the training and validation accuracy on the bottom right. And while there was some overfitting that you can see there below, I tried increasing the dropout rates and regularization strength and found that this resulted in a lower validation accuracy. So my conclusion here was that in order to further increase accuracy and reduce overfitting, more drastic changes to the model architecture, the data preprocessing, or the training approach might be necessary. And so again, you can see the confusion matrix above. It does very well on classical and metal, as well as jazz. And generally, this model is just doing better than all of the prior models, again, as indicated by the accuracy, which is notably higher. So finally, we'll discuss some takeaways and some opportunities for future work. So the KNN and SVM models had a relatively high accuracy of 68 and 67% respectively, but these also had a very low computational cost. And we proved that they could be improved slightly with added training data. So my recommendation would be, if you have limited computational resources and you have some leeway on accuracy, these would be the models to pursue. However, if you're striving for the highest accuracy and you have access to more compute, then the convolutional neural network has a much higher ceiling, it appears. I would also say that logistic regression is not feasible, as it's not possible for it to improve enough to close the gap between KNN and SVM. Finally, some things that were consistent between models were that classical and metal were the easiest to identify, and country and reggae were the most challenging to identify. So I found that interesting that this remained consistent between models. Finally, some opportunities for future work. The traditional machine learning models could have their accuracies improved by increasing the training dataset size. And because the spectrograms are just representations of wave files, and the same can be said for the tabular data, having access just to a wave file should be able to allow you to increase the dataset size, assuming you can label the genre of the data. Finally, I found it interesting that you could extract a histogram from each spectrogram's intensities, so modeling the frequency of different intensities across the spectrogram. Now, I thought this would make an interesting addition to the tabular dataset if you could represent this histogram in that way. I've done something similar in a robotics project and thought this would be interesting, although you are losing the time-dependent nature of the data, in that the spectrograms, as you proceed from left to right, that is the dimension of time, and a histogram is simply collecting the frequency of all intensities across the entire spectrogram, time not being considered. So this would make an interesting addition to see if this performs better or worse, if it helps the models. I'll be interested to proceed with this later on. But that sums up my project. And so, as promised, here are the references. The first of these is the dataset itself, and the second is a paper that I used as reference. And so I hope you enjoyed my project. I had a lot of fun working on it, so I'd be interested to see if anyone can take this further.